right. Welcome to the last section for today. And our next speaker is going to be Shah, who will talk to us about the auxiliary field deformed E model.
All right. Thank you very much for giving me this opportunity to talk a little bit about my work here, and also thank you to all the organizers for actually making us able to see what everyone is going to present a bit more clearer. So thank you for that. And yeah, I'll be talking about auxiliary field deformed E models, which is based on some recent work, which hopefully will be out soon with them. So let me start with giving a little bit, talking a little bit about the motivation behind this work, motivation behind studying auxiliary field sigma models. So it's fairly recent work. Just 2 years ago, this huge class of integrable deformations of 2D sigma models was constructed by Chris and Liam. And since then, to talk a little bit more about this, it's understood as a sort of a generalization of TT bar-like deformations. And since then, since these past 2 years, it has become quite an active area of work where bunch of new directions have been sprouted out from this area. So exactly what I was talking about. So in these 2 years, you can see a bunch of examples have come into existence where auxiliary field deformations have been studied from the point of view of PCM with having Wisdom origin term for a non-abelian T-dual, abelian T-dual, Young-Baxter deformations, some concept pictures as well. And then on the other side, understanding what auxiliary field deformations could be from the 4D Chern-Simons side, and some recent work on Courant-Hilbert construction as well, and many more ideas if I've failed to put in an extra bubble there. So yeah, it's a growing field. And now, because it's quite a growing field, let's try to dig a bit deeper into this. And so the motivation is for my work is that E model has been known to be the underlying sort of a connecting link for all these bubbles that I was just talking about. It has been known to be something that connects to all through these bubbles. But for the undeformed cases, so the idea is that what if the same connecting link can survive for the deformed cases as well, which can lead to the unification through having an auxiliary field deformed E model itself. So instead of studying these tiny bubbles on their own, you can just think of it as a whole complete unified picture that can be addressed. Which leads to another question, that what would be the thin-film double implementation for these auxiliary fields, and we'll be diving in to more details for that. So yeah, this is exactly what I was trying to say, that these bubbles are on their own, but now we can actually look at all of them through the lens of auxiliary field deformed E model. So just to give a little outline of the talk, I just talked about the motivation behind this work. And to give a little bit of introduction, I would be reviewing what exactly auxiliary field sigma models are, what are the different tools that you will need to actually construct the auxiliary field deformed E model, and then we'll be looking at its construction. And then, of course, we have integrability, question of integrability. Once we have some new model, we do want to look into that. So I'd be talking about integrability of this model, and then moving on, I would be talking about some new bubbles that have shown up because of having a much broader picture at hand. And then I would just conclude with a little bit of summary of the work, and then with some new possible extensions of this work. All right, so diving into the introduction of auxiliary field sigma model. As I was saying, it's been recently constructed 2 years ago, integrable deformation of sigma models using auxiliary fields. So if it is familiar to you guys, this can be thought of as some reincarnation of the Ilmenau Supnic construction, which was done for the four-dimensional case, but now you do it at the level of 2 sigma models. So that was the little bit of history or origin motivation for these models. So the idea is that you can start with a simple principal Cairo model action, and then introduce an additional Lie algebra valued auxiliary field, the ones in red, these little v's in this way, along with an interacting function, which depends on this little mu, which takes this particular form. So the idea is that, let's say you want to go back from the deformed case to back to what you started with. All you need to do is you turn off the interaction function, integrate out the auxiliary fields, and then you would go back to PCM. That's how you would recover it. And as I was mentioning earlier, these are thought as an equivalent to all stress energy type tensor deformations of PCM. Now, that's one of the tools that we will need to understand the construction of auxiliary field deformed E models. But the another tool that we need to know is just going back to how PCM can be actually uplifted to the E model at the Drinford double level. So once again, let's say you start with PCM, just like this, sitting on some regroup G. And then what we can do is case the right global symmetry with some Lagrange multiplier, which will enforce the flatness of these gauge fields. Then you can gauge fix one of the components, integrate out the others into the process, and then you end up with an action that looks something like this. So you not just have J, but also these Lagrange multipliers, phi. And this, in fact, is nothing but the E model action which sits on the double. And to actually visualize how that works, let's look at the original action for E model given by Klimchik back in the day, which looks something like this. So you take this ln, which sits on the double, and if we decompose it in this way and use this linear map, which was the name is based on E model, we take this linear map E, which is self-adjoint and idempotent in a particular way. And this, once you solve it, it will actually go back to this. So these two are pretty much the same things. So that's pretty much the idea as to how you can uplift from, how you can go from PCM to E model level. So now let's try to use these two tools in order to construct auxiliary field deformed E model. As I was saying, that this is what we started with. We saw how we can take PCM and deform it to go to the auxiliary field deformed model. And apart from that, we can also uplift this to look at the E model level. But now the idea is that what if we uplift this and that actually gives us the deformed version of E model itself. So the idea would be that instead of starting with the PCM, we start with the deformed model instead, and then perform the same gauging trick as before, which will now give us some Lagrangian. Instead of just J and phi, it would have the auxiliary field V present in it as well. And then we try and interpret that at the Drinford double level and what that action would look like. And in order to do that, we will need to understand we will need to introduce a Drinford double valued auxiliary field as well. So this corresponding to what we had here, instead of this, now after performing the same gauging trick, we end up somewhere here. So as you can see, we still have the same undeformed terms showing up, but now we have one extra piece which has the auxiliary field V sitting in it, and along with its interacting function. But now this new looks a bit different because, as again, now everything is sitting at the Drinford double level. So this new looks something like this. Now, in order to go back to PCM or the group level, you will need to see how the decomposition for this Drinford double valued auxiliary field V would look like as well. And let's say if you take this, it will identify the double picture of the PCM auxiliary field. So you take this, take this V and once again decompose in the same way, and that will take you to the uplifted Lagrangian, which is in terms of not just J, phi, and phi as well.
Sorry, question.
Yes.
This new expression in terms of big V and epsilon, why is it this expression? What's that for?
Oh, okay. Good question. So as we saw earlier, there we go. So this E nu interacting function, this nu needs to take a particular form of this. So in order to retain this structure, when you boil it down from the double to the group level, that's why we have that structure of E. All right, and just as we saw in the case of auxiliary field sigma model, just at the PCM level as well, the check is that once you turn off the interacting function and integrate out the auxiliary fields, you should be able to recover the E model or the PCM that you started with. So same thing happens here as well. If we set E due to 0 and take V on shell, we would recover the original E model. Now, something interesting happens when you're working at the Drinker level picture. The other bubble that we saw, which was having auxiliary field deformations along with the non-abelian field, but this particular case just happens to be a bonus at this stage. If you switch the decomposition of the Drinker double valued field L, it would give you the non-abelian T-dual, and this is indeed known for the undeformed case, and it actually follows that if you do this, even for the deformed case, it reproduces back the auxiliary field deformation for the non-abelian T-dual, which was done in the last 2 years by Daniele, Chris, Liam, and Gabriele. So now, if we want to look at more complex examples of the Drinker double, we will need to consider the second order action for the auxiliary field deformed T model. And in order to do that, let's once again start by looking at what we have at hand, which is the first order action. And then we redefine L in this way so that we can have our second order action sitting on the coset. And this can be done by introducing a projector P, just as we do for the undeformed case as well, where this projector P is defined by these two conditions. And once we have that, we go back to the second order action for the auxiliary field deformed E model, where once again you can see that the term number 1, 2, and with the bulk piece, it's all pretty much similar to what we have for the undeformed case, but now we have these new terms popping up which have V sitting in them, and it's quite similar to what you have for the very first auxiliary field sigma model that I was talking about, where you have a piece which is linear in V, but then there are pieces which are there are two V's present in them, and then once again we have the same old interacting function E. Now, as I was saying, the check needs to be that once you turn off this interacting function and integrate out the auxiliary fields, you should get back the undeformed cases. And it so happens that here this works through as well. You turn this off and integrate out the auxiliary field. We recover the known second order action for the E model. Any questions so far? All right, so now let's move on to the question of integrability for these new action that we have. So back in the day, almost a decade ago, Shah came up with this nice mechanism where instead of going at the group level, just by saying at the principal level, without choosing particular examples, you can actually find out a general construction for what the last connection needs to be. So let's just go through quickly with what that construction is, because we'll be using that to address the question of the deformed cases as well. So the setup is that we have a PL type sigma model on the coset, where we have these two little subspaces V plus and V minus. And everything is depending on these little a's. So to dive deeper into this, what the idea is that the solutions of the equations of motion can be equivalently encoded into the flatness of A. So we have this one form A, which is supposed to be flat, but more than that, it also needs to satisfy this one extra condition where it decomposes in this certain way. So A plus sits in this subspace of B plus, curly B plus, and A minus sits in this curly B minus. And once we have the flatness of A, that can lead us to coming up with a linear map P and its flatness such that it obeys this particular condition. So the idea is that once we have this is all about having the existence of this linear map P. And once we have that, we can generate a family of this, and then that should essentially lead you to have a flat-flex connection. One diameter family. So now that was all about the existence of it, and in order to actually define what this P is supposed to be, let's try and understand how that goes. And in order to do that, we need to, let's say you take the Drinford double, which can be written in this way, where W can take these examples where to point out to something similar, taking the first case that would lead you to having the Young-Baxter deformation, going for the second case that would lead you to have the lambda deformation, and the last one would give you either PCM or the non-ability dual part. So we can define this particular linear map P in this fashion, where it pretty much depends on the other map Q, which satisfies a condition like this, where these little E pluses and minuses, they sit in curly V 0 plus minus, and there are some non-zero elements that you can choose for every particular example of the double that you're working with. And once we have that, the idea is the solutions actually form a curve, which give us a one parameter family of QZ, and then essentially which leads us to having some idea of how the lax is supposed to look like. And we can decompose our one-form current in this particular way to identify what L plus and L minus need to be, and then eventually have this final lax, one parameter, which is coming from the QC here that we have particularly. So this is sort of a little sketchy way of understanding how the mechanism back in the day was thought about for undeformed cases of E-models. Now, what would happen if you're using the same procedure but for the deformed cases? So for the deformed cases, all we need to understand is everything depends on having a flat A and it better decompose in this way. Those are the two conditions that we need to satisfy. For the deformed cases, the flatness works immediately. It still holds, but this decomposing, this grading condition is no longer automatic. So in order to have that, we still need to understand that there's one tool that we need to use always, that we take auxiliary fields on shell. And when we do that wonderfully, it does go back and we see. So as you can see, this equal and dot just means that you are taking on shell, the equation is on shell, and this little curly E plus minus is something that takes you to these subspaces B plus B minus. So eventually, this A plus minus actually does land back into the same grading that we want, but it is on shell. And instead of just having A being decomposed into A plus and A minus, now instead, as you can see right here, that it's not just A plus and A minus, there are these two components still present, even on shell, but you can write them in this way. Algebraically speaking, it still does land into the subspace that we want. And if one can also do a little dynamical change of coordinates to make the proof go through. Yeah.
Parita, I'm not sure I really understand. What was this P? You mentioned that for the PCM, your double is just G plus P. So what's P in that case?
You mean this?
Yeah, what's P?
Okay, so so P, no matter what case you're working with, it will still be defined in this way. It's defined in the way of a Q, the map Q, and the Q needs to satisfy this condition. And then depending on what W is, these E plus E minuses would look different.
Would you mind telling me, Gina, I happen to know off the top of your head a simple example with like the PCM or something?
Oh yeah, of course.
If it's too complicated, then I can't start.
Yeah, but okay. So for example, for the case of G plus T, it would look like you can take E plus E minus as 1 comma T and T comma 1, where T is just a parameter, and then it would, yeah, this condition like still follows through, it still satisfies. And then it's not about having P is something which is internal in the proof, so you never actually work with P. Q is something that you're working with. So that's why P is always defined like this.
Yeah, thank you.
Yeah, we can talk later if
Thanks.
that doesn't answer your question. All right, so as I was saying that now it's not just that A plus and A minus, but A plus itself again is decomposed into 2 pieces like this, and A minus again decomposed into 2 pieces. But the idea is that when we take things on shell, the grading still works, the proof still works, and we can eventually find the lax just like this. So the Shivera mechanism actually can be generalized to auxiliary field deformed cases as well when you take them on shell. And now you can think that, okay, this still looks similar to what we had in the undeformed case. What's the difference? Where are the auxiliary fields? So in order to understand that, as you can see, there are these little L pluses and L minuses sitting there, and that's where the auxiliary fields will come into the picture. And once we use the decomposition of L like this, and because we want the last on the group G, you would have to integrate out the G tilde part. And in order to do that, we use the equation of motion, and that is where the V shows up in the picture. And then we can compare it with the decomposition of L plus and L minus, and then that's how we can plug things back, and we would have a Lux which has relief. So to go over some of the examples, we do in fact recover when we take the Drinfeld double of which is known to give us the Young-Baxter case, we do recover the auxiliary field deformed Young-Baxter model just like this. And by using the Lux formula, which is given from the generalized Shivera mechanism, we do in fact obtain these pieces. These are, you can think of this as the L plus and L minus that we saw in the equation. And this matches with the guess of the Lux that the group had for their work as well. And if you take the limiting case, it does reproduce the results of the PCM as it should. Now, because we're working with the generalized picture, we can go for the lambda deformation. And if we take this double and use the known information of the map E and P, we do in fact not recover, but we do obtain the lambda deformation case as well. But as you can see, we do need to use this V interpretation of auxiliary at the Drinfeld double level. And this is the auxiliary field deformed lambda deformation case that we got. Okay, I should hurry up. So once again, as the check was that if we take things on shell and you put E to 0, we do in fact recover the lambda deformation case. And once taken the limiting case, it goes to the auxiliary field deformed non-negative dual part. And the Lux mechanism does indeed generate things in this way. The equations look like this. And the check is that when you take auxiliary fields on shell, these pieces, J plus and curly J plus minus, they do obey these certain conditions, which indeed lets the Lux to be flat. And the Shivera mechanism naturally decomposes things into a flat piece and a conserved piece. So to quickly conclude what I was talking about, we see that we can actually uplift the auxiliary field deformation to the Drinfeld double level. This unifies all the different bubbles that have come up in the past 2 years. The Shimura mechanism can be extended, and even not just the extension, but it gives a deeper insight to, it's not a guess at what these flat intensive quantities are supposed to be. It comes out of the construction, it directly gives you that. And we also have a new example, which is the auxiliary field deformed lambda module case. And there are some immediate extensions that one can think about. There has been some work done where 4D Simons is connected with auxiliary fields, but it would be nice to look at it through the idea of E model. There's already been some work in progress with Gabrielian group, and then on Courant-Hilbert type of construction from the E model perspective, and other extensions could be looking at the higher spin deformations or positive cases for at the level of principal double, and that'd be interesting to see as well. Thank you.
Okay, thank you, Parita. We would have any questions? Yes.
The talk. So this idea that the Severus condition also works for auxiliary, does that relies on the particular structure of the Drinfeld double that you chose here, this G tensor W, or would that work for any Drinfeld double with any E?
So this is
This structure here.
this is the structure that was used in the undeformed mechanism, and we just worked with that.
Well, that's very specific integrable model, but there are some with way more complicated E and Drinfeld double.
But yeah, that's a good point. I suppose if it can be done for the undeformed, just with working with D and not having this decomposition. If it can still be done for the undeformed case, it would be, then that gives us hope to look at the deformed cases. But yeah, because at this level of the proof, this is the decomposition which was used, and we followed the similar decompositions.
All right.
Thanks. Thank you for the talk. I wanted to ask, you mentioned that the higher spin cases would be interesting. Could you highlight maybe where the fact that you're working with the stress tensor type deformations appeared, and how you might hope to generalize that to the higher spin case?
Okay, so the higher spin cases, so everything. Okay, right here. So yeah, I guess it all depends as to how we can write this particular structure of nu in terms of the Drinfeld double. As you can see, it needs to have two pieces, and it would be hard to get structures which are like trace V plus power n, where n is, let's say, something odd. But you can perhaps introduce some operators which just picks out one piece, and yeah, it's like about having the interpretation at the double level.
Thank you.
Sorry, just to add one more comment. I guess the let's say, for example, you were talking about the TT bar type of case. It all goes down to what type of function you're choosing. So for particular choice of E nu, you would recover, let's say, TT bar or TT bar. And you choose those particular functions, and then you boil it down to the group level, and that's where you will see those deformed pieces.
All right. If there are no further questions, let's thank our speaker again.